The Arctic, 2024. A drilling rig bites into Siberian permafrost that's been frozen for thousands of years. The thermometer reads 2 degrees Celsius above normal. Not catastrophic, not yet. But when the drill pulls back up, something else comes with it. Bubbles. Methane, trapped in ice since the last ice age, now fizzing to the surface like a shaken soda can. The scientists watching know what this means. They've seen the graphs, run the models, studied the ancient climate records. And those records tell them something unsettling. This has happened before, 56 million years ago to be precise. Methane erupted from the ocean floor, temperatures spiked, and the planet lurched into a fever that lasted hundreds of thousands of years. But that catastrophe, as we'll see, was just the second act. To understand what's happening in the Arctic right now, we need to go back even further, 10 million years further, to the day the age of dinosaurs ended and the age of mammals began. To the day an asteroid the size of Mount Everest slammed into the Yucatan Peninsula at 20 kilometers per second. The Yucatan, 66 million years ago, 10 seconds before impact. A Tyrannosaurus rex stands on the shore of a shallow inland sea, its massive head scanning the water for prey. Pterosaurs wheel overhead, their wingspans stretching up to 10 meters. In the warm waters, ammonites spiral through the depths, their chambered shells catching the sunlight. There are roughly 300 species of dinosaurs alive at this moment, spread across every continent. The planet is warm, lush, and teeming with life. The air is thick with oxygen. The forests are dense with flowering plants that only evolved 20 million years earlier. And the food chains are complex, stable, finely tuned by 160 million years of dinosaur dominance. And then the sky catches fire. The asteroid enters the atmosphere at a shallow angle, compressing the air in front of it so violently that it heats to several thousand degrees. For one brief moment, anyone looking up would see a second sun streaking across the sky, brighter than anything that has ever existed on Earth. But there's no time to process what's happening. The asteroid covers the distance from the upper atmosphere to the ground in less than 2 seconds. When it hits with the force of 10 billion Hiroshima bombs. Not metaphorically, that's the actual calculation. The impact excavates a crater 180 kilometers wide and 20 kilometers deep in less than a minute. Rock that has been solid for millions of years vaporizes instantly. The shockwave radiates outward at supersonic speed, flattening everything within 1,000 kilometers. Trees, animals, mountains, all swept away like dust. But the real killing hasn't even started yet. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. Within 10 minutes, a wall of water 300 meters high races across the Gulf of Mexico and the Atlantic. Tsunami isn't the right word for this. This is the entire ocean rising up and slamming into the continents. Everything within 500 kilometers of any coastline is scoured clean. But you'd have to be extraordinarily unlucky to die in the tsunami, because within an hour, something worse begins. The asteroid didn't just vaporize rock, it vaporized sulfur-rich minerals from the ancient seabed. That sulfur, mixed with water vapor, forms sulfuric acid in the upper atmosphere. Within hours, it begins to fall as rain. Not rain with a pH of 5 or 6, like modern acid rain. Rain with a pH near 0, battery acid falling from the sky. Lakes and rivers turn to acid. Plants dissolve. anything with exposed skin or gills dies in agony. And then there's the heat. The rock and debris ejected into space doesn't stay there. What goes up must come down. And when trillions of tons of superheated rock re-enter the atmosphere, they heat the air to the temperature of an oven. The entire sky glows red. Forests across the planet spontaneously ignite. Within 12 hours, 70% of the Earth's surface is on fire. But here's the thing that's hard to wrap your mind around. The asteroid itself, the tsunami, the acid rain, the global firestorm, none of that is what kills most of the dinosaurs. What kills them is what comes next. The sky fills with ash and soot. The sun disappears. And the temperature drops. Impact winter. Think of it like nuclear winter, but worse. The dust and ash from the impact and the fires block out so much sunlight that photosynthesis essentially stops for 2 years. Plants can't grow. Herbivores starve. Carnivores starve. The global temperature drops by 30 degrees Celsius in a matter of months. The planet, which had been a warm, tropical paradise, becomes a frozen graveyard. In the Hell Creek Formation in Montana, we can see this moment frozen in the rock. There's a layer of sediment that contains the last dinosaur fossils. Above it, nothing. Just a thin band of clay rich in iridium, an element rare on Earth but common in asteroids. And above that clay layer, no dinosaurs. Ever again. But there's something else in those rocks. Something extraordinary that most people don't know about. In Tanis, North Dakota, paleontologists have found fish with asteroid fragments embedded in their gills. These fish died within an hour of the impact. Not from the shockwave, not from the heat, but from breathing in tiny spherules of molten rock that fell from the sky like deadly hail. They preserved a snapshot of the first hour of the apocalypse. The impact winter lasted at least 2 years, maybe longer. When you're a 50-ton sauropod that needs to eat half a ton of vegetation every day to survive, 2 years without food is a death sentence. When you're a Tyrannosaurus rex that needs to hunt large prey, and all the large prey is already dead, you're not far behind. The last dinosaurs didn't die in fire and fury. They died slowly, cold and starving, in a world that no longer had a place for them. But not everything died. And this is where the story gets interesting. Because the survivors, the organisms that made it through the impact winter, followed a very specific pattern. There was a rule. We call it the 25-kilogram rule. If you weighed more than 25 kilograms, roughly 55 pounds, your odds of survival were essentially 0. If you weighed less, you had a chance. Not a guarantee, but a chance. Why? Because small animals need less food. A mouse can survive on seeds and insects and scraps. A T-Rex needs hundreds of kilograms of meat, and there is no meat. Small animals can hide underground, in burrows where the temperature stays relatively stable even when the surface is freezing or burning. Large animals can't. Small animals can go dormant, lower their metabolism, wait it out. Large animals burn through their reserves and die. It's brutal arithmetic, but arithmetic doesn't care about fairness. So, who made it? Mammals, obviously. But not the mammals you're imagining. Every mammal alive ATD of the Cretaceous was small. The largest was about the size of a badger. Most were the size of rats or mice. They were nocturnal, they ate insects or small plants, and they lived in burrows or dense underbrush. They were, by dinosaur standards, completely insignificant. Until the dinosaurs were gone. Birds survived, but not most birds. The fossil record shows that only a few lineages made it through. specifically the ones that lived near water or on the ground and could eat seeds. When the forests burned and the plants died, seeds survived. Seeds are designed to survive catastrophe. They can lie dormant for years, waiting for conditions to improve. The birds that could eat seeds, that could crack them open and digest them, had a food source when almost nothing else did. The rest, the tree-dwelling specialists, the insect eaters, the large flightless forms, they vanished. Crocodiles survived. All of them. Every single lineage of crocodilians alive at the end of the Cretaceous made it through to the other side. How? Crocodiles have a superpower that most people don't know about. They can go an entire year without eating. They slow their metabolism to almost nothing, sit at the bottom of a river or swamp and wait. When the impact winter hit and the food chains collapsed, crocodiles just turned off and waited for the world to restart. Turtles survived. Amphibians survived. Freshwater fish survived better than marine fish. And insects, despite the fires and the cold and the lack of plants, barely noticed. Insects can breed so quickly, can adapt so fast, that even a 90% die-off just means the survivors repopulate in a few generations. But here's the detail that should make you pause. Mammals didn't just survive, they were ready. For 160 million years, mammals had been living in the shadow of dinosaurs, small and nocturnal and almost invisible. But they had been evolving all that time, developing better hearing, better smell, more efficient metabolisms, more complex brains. They were already adapting to a world where you had to be clever and quick and opportunistic to survive. And when the dinosaurs disappeared, mammals stepped into the void. But they didn't step into a paradise. They stepped into a wasteland. The first 10,000 years after the impact were dominated by ferns. Not trees, not flowering plants, ferns. We know this because there's a geological layer found all over the world called the fern spike. It's a band of rock from the early Paleocene that contains almost nothing but fern spores. Millions upon millions of them, packed so densely that they form a visible line in the cliff faces of places like Wyoming and North Dakota. Why ferns? Because ferns reproduce with spores, and spores are nearly indestructible. They can survive fire, freezing, drought, even the vacuum of space. When the impact winter ended and the sun finally broke through the ash clouds, fern spores that had been lying dormant in the soil for years suddenly germinated. Within weeks, the planet was covered in a carpet of ferns. No trees, no flowers, no grass, just endless fields of waist-high ferns stretching to every horizon. It looked, quite literally, like the Devonian period, 350 million years earlier. The planet had been knocked backward in time. But ferns are just the opening act. They stabilize the soil, they add organic matter, they create the conditions for other plants to return. And slowly, over thousands of years, the forests came back. First conifers, tough and resilient, able to grow in poor soil. Then flowering plants, faster growing, more diverse, better at attracting what few pollinators were left. Within 100,000 years, the world was green again. Different green, but green. And the mammals? They were watching, waiting, evolving. The earliest Paleocene mammals were still small. The largest was about the size of a beagle. They had names like Purgatorius, which is fitting because they emerged from a literal hell. Purgatorius was one of the earliest primates, one of our direct ancestors. It was about the size of a mouse ate insects and fruit and lived in trees. Not impressive by modern standards, but it survived. And survival is the only currency that matters in evolution. But here's where the story takes its first unexpected turn. Evolution after the asteroid didn't just continue, it accelerated dramatically. Before the impact, new mammal species evolved slowly over millions of years. The ecological niches were full, competition was fierce, and there was no room for experimentation. But after the impact, the niches were empty. Every role that dinosaurs had filled, herbivore, carnivore, scavenger, every size class from tiny to enormous, was suddenly up for grabs. And mammals, for the first time in their history, had the opportunity to fill them. In the Maynard Formation in France, paleontologists have uncovered one of the most complete post-impact ecosystems ever found. It dates to about 100,000 years after the asteroid, and it contains over 100 species of mammals. 100 in one location. Before the impact, that same area would have had maybe 10 or 15 mammal species, hiding in the undergrowth, trying not to get stepped on by dinosaurs. Now they were everywhere. Small ones, medium ones, ones with specialized teeth for eating insects, others for crushing seeds, still others for slicing meat. Evolution was experimenting, trying every possible variation, seeing what worked. And the pace was astonishing. New species were appearing every 10,000 years. In normal times, it takes 1 to 2 million years for a new mammal species to evolve. But this wasn't normal times. This was chaos. And chaos, it turns out, is an incredibly powerful evolutionary force. Within 1 million years, the first large mammals appeared. And by large, I mean the size of a sheep. That doesn't sound impressive until you remember that just 1 million years earlier, the largest mammal was the size of a rat. The size increase happened 5 times faster than normal. These early giants had names like Pantolambda, a strange, bulky creature with a long tail and 5-toed feet, probably omnivorous, eating whatever it could find. It wasn't graceful, it wasn't specialized, it was just big. And being big in a world without large predators was enough. Then came the carnivores. Arctocheon, a bear-like predator about the size of a wolverine. It had powerful jaws, sharp teeth, and the build of something that could take down prey its own size. It was one of the first mammals to fill the role that dinosaurs had left empty: apex predator. But here's the thing. Arctocheon wasn't related to modern carnivores like dogs or cats. It was part of a completely different lineage, one that would eventually go extinct. Evolution was throwing everything at the wall to see what stuck. And some of what stuck was genuinely bizarre. There were herbivores with claws, carnivores with hooves, omnivores with teeth so strange that paleontologists still aren't sure what they ate. These were evolutionary experiments, dead ends, nature trying out ideas that wouldn't work in the long run, but were good enough for the moment. The Paleocene was evolution's rough draft. But the world they were evolving in wasn't stable. The climate was swinging wildly. The asteroid had injected so much sulfur into the atmosphere that it caused a brief ice age. But once that sulfur washed out, the greenhouse gases that had been building up from volcanic activity took over. Carbon dioxide levels soared to 1,000 parts per million. For reference, we're currently at 420, and that's already causing significant warming. 1,000 parts per million meant the planet was hot, very hot. There were no ice caps, none. Not at the North Pole, not at the South Pole, not even in the mountains. Palm trees grew in Alaska. Crocodiles swam in the Arctic Ocean. The global temperature was 12 to 14 degrees Celsius warmer than today. The equator, which is already hot now, was pushing 35 degrees Celsius year-round. Anything that couldn't tolerate heat either adapted, migrated, or died. And yet, life found a way. It always does. The forests of the Paleocene were unlike anything we have today. In what is now Big Bend National Park in Texas, paleontologists have found fossilized palm trees, their fronds perfectly preserved in stone. These weren't small palms. They were massive, 30 meters tall, forming dense tropical forests that stretched across what is now desert. The world was a jungle from pole to pole. But here's the detail that most people miss. There was no grass. None. Grass wouldn't evolve for another 40 million years. The Paleocene was a world of forests, ferns, shrubs, but no grasslands, no savannas, no prairies. Every ecosystem was dominated by trees, which meant that every herbivore had to be either a browser, eating leaves from trees, or small enough to live in the undergrowth. The large, grazing megafauna we associate with mammals, the bison, the horses, the antelope, didn't exist yet. They couldn't. There was nothing to graze on. And the mammals, freed from the constraints that had held them back for so long, began to diversify in ways that were wildly different depending on where they were. Because here's something crucial to understand. The continents were separating. When the asteroid hit, the world's land masses were already drifting apart, but slowly. By the Paleocene, they were isolated enough that evolution on each continent began taking its own path. In North America, a group of mammals called the condylarths were experimenting with being herbivores. Phenacodus, a wolf-sized animal with 5-toed feet and a long tail, was one of the most common. It had simple, low-crowned teeth, suitable for eating soft leaves, and it moved through the forests like a clumsy deer. It wasn't related to deer. It wasn't related to any modern herbivore. It was just the first mammal to figure out how to make a living eating plants. In South America, something stranger was happening. The continent had separated from the rest of the world, and its mammals evolved in complete isolation. Instead of placental mammals, which give live birth and nourish their young through a placenta, South America was dominated by marsupials. These weren't like the kangaroos and opossums we know today. These were predators, sparacidons, marsupial carnivores with blade-like teeth and powerful jaws. They evolved into the ecological role of wolves, lions, and saber-toothed cats. But they did it completely independently. It's a perfect example of convergent evolution. Give a continent 10 million years and an empty niche, and it will evolve something to fill it, even if that something comes from a completely different family tree. In Europe, which was mostly a collection of tropical islands surrounded by the shallow Tethys Sea, mammals were smaller and more diverse. There were gliding mammals, semi-aquatic mammals, tree dwellers and ground dwellers, and crocodiles. Enormous crocodiles, some over 6 meters long, hunting in the warm coastal waters. For a brief window, crocodiles were the dominant predators of the European seas, because the marine reptiles that had ruled during the age of dinosaurs, mosasaurs, and plesiosaurs had gone extinct along with their terrestrial cousins. Asia, meanwhile, was connected to North America through the Bering Land Bridge, which allowed mammals to migrate back and forth. This genetic and ecological exchange meant that Asian and North American mammals were more similar to each other than either was to South America or Europe. It's why, millions of years later, animals like camels, which evolved in North America, would eventually migrate to Asia and survive there long after they went extinct in their homeland. And then there was Antarctica. Today, Antarctica is a frozen, lifeless desert. But in the Paleocene, it was green. Temperate forests of southern beech trees covered the coasts. Marsupials, relatives of modern Australian possums, lived in those forests. There were no ice sheets, no glaciers, nothing even close to frozen. The entire continent was habitable. It wouldn't stay that way forever, but for now, it was just another piece of the global ecosystem. But the most astonishing thing about the Paleocene wasn't how different these continents were. It was how fast everything was changing. 5 million years after the asteroid impact, mammals had gone from rat-sized scavengers to sheep-sized herbivores to bear-sized predators. That's an evolutionary explosion. The kind of rapid diversification that normally takes 50 million years happened in 5. And it wasn't slowing down. It was accelerating. By 58 million years ago, 10 million years after the asteroid, mammals had reached sizes that would have been unthinkable just a few million earlier. Barolambda, a herbivore found in Wyoming, weighed as much as a modern rhinoceros. It had a heavy, barrel-shaped body, short legs, and 5 clawed feet. It wasn't fast. It didn't need to be. There were no large predators capable of taking it down. It just wandered through the forests, eating leaves and growing fat. But it wasn't just mammals that were getting big. Birds were experimenting with size too. In Europe and South America, large, flightless birds began to appear. These were the ancestors of what would later become terror birds, apex predators that stood 3 meters tall and could run down prey at 40 kilometers per hour. But even in the Paleocene, some species were already approaching 2 meters in height, armed with massive hooked beaks capable of crushing bone. They weren't dominant yet. That would come later. But they were there, watching, waiting for their moment. And in the rivers and swamps, crocodiles reigned supreme. Dinosaurs, a 6-meter-long crocodilian with a narrow, gharial-like snout, hunted in coastal waters from Africa to South America. It survived the asteroid impact without breaking stride, and now it was thriving. But what's truly extraordinary is what would come just a few million years later, in the early Eocene. In the tropical swamps of what is now Colombia, a snake evolved that makes every modern reptile look insignificant. Titanoboa, 13 meters long, weighing over a ton, the largest snake that has ever existed. To put that in perspective, the largest anaconda ever measured was about 9 meters. Titanoboa was half again as large and proportionally much heavier. It lived in rivers and swamps, hunting crocodiles, turtles, and large fish. It could swallow a human whole without even noticing. But Titanoboa wasn't just impressive because of its size. It was impressive because of what its size tells us about the world it lived in. Snakes are cold-blooded. Their body size is directly linked to the ambient temperature. The warmer the environment, the larger they can grow. For Titanoboa to exist, the average temperature in northern South America had to be at least 30 to 34 degrees Celsius, year-round. That's 10 to 12 degrees hotter than the same region is today. The Paleocene and the early Eocene that followed wasn't just warm, it was sweltering. And that warmth was about to get worse. Because 5 million years into the recovery, just when ecosystems were stabilizing, when mammals were settling into their new roles, when the world seemed to be finding a balance, the climate went haywire. Again. But this time, there was no asteroid. This time, the planet did it to itself. The trigger was volcanic. The North Atlantic Igneous Province, a chain of massive volcanic eruptions stretching from Greenland to Iceland, began pouring lava and carbon dioxide into the atmosphere. These weren't ordinary eruptions. This was flood basalt volcanism, where magma wells up from deep in the mantle and spreads across the landscape like water from a broken dam. Millions of cubic kilometers of lava erupting over the course of millennia. And with the lava came carbon dioxide, enormous amounts of it. Enough to raise the global CO2 concentration from 1,000 parts per million to 2 or even 3,000. But even that wasn't enough to explain what happened next. Because at some point, around 56 million years ago, the ocean itself started releasing carbon. Beneath the seafloor, in the cold, high-pressure depths, methane doesn't exist as gas. It exists as methane hydrate, a solid crystalline structure where water molecules trap methane molecules in a frozen lattice. It looks like ice, but if you light it on fire, it burns. These hydrates are stable as long as the water stays cold and the pressure stays high. But if the water warms even slightly, the hydrates destabilize. The methane escapes. And methane is a greenhouse gas 25 times more powerful than carbon dioxide. When the North Atlantic volcanoes warmed the deep ocean by just a few degrees, they set off a chain reaction. Hydrates melted. Methane bubbled to the surface. The methane trapped heat. The heat melted more hydrates. More methane, more heat. A feedback loop that, once started, couldn't be stopped. We can see this event written in the rocks. All over the world, in marine sediments from the late Paleocene, there's a sudden dramatic shift in carbon isotopes. The ratio of carbon-12 to carbon-13 drops sharply, and that drop is the signature of methane release. It's as clear as a fingerprint. Between 2 and 7,000 gigatons of carbon entered the atmosphere in less than 20,000 years. To put that in perspective, humanity has released about 1,700 gigatons since the Industrial Revolution began. The Paleocene-Eocene thermal maximum, or PETM as it's called, was 4 to 5 times larger. And the planet responded exactly the way you'd expect. Temperature spiked, not gradually, not over millions of years. Over 10 to 20,000 years, the global average temperature increased by 5 to 8 degrees Celsius. In the Arctic, it increased by 23 degrees. The Arctic Ocean, which had been cool but not frozen, became as warm as the modern Gulf of Mexico. Palm trees, mangroves, crocodiles all thrived in polar regions. The planet had entered a state of extreme greenhouse conditions, and there was no off switch. The oceans bore the brunt of it. When you pump that much carbon dioxide into the atmosphere, a significant portion dissolves into seawater. And when CO2 dissolves, it forms carbonic acid. The pH of the ocean dropped from 8.2 to somewhere between 7.6 and 7.8. That might not sound like much, but pH is a logarithmic scale. A drop of 0.4 means the ocean became 60% more acidic. Anything that built its shell out of calcium carbonate, foraminifera, mollusks, some plankton, struggled. In the deep ocean, where the pressure makes calcium carbonate even more soluble, between 30 and 50% of foraminifera species went extinct. These are single-celled organisms, microscopic, but they are the base of the marine food web. When they die, everything above them suffers. But on land, the situation was different. Extinctions happened, but they were relatively mild. Maybe 10 to 15% of mammal species disappeared. Which raises an obvious question. If the ocean was in crisis, why was the land okay? The answer is migration. When the temperature soared, ecosystems didn't collapse. They moved. Tropical species migrated toward the poles. Temperate species, which had been living in the mid-latitudes, followed them north. And the polar regions, which had always been cool and relatively barren, suddenly became biodiversity hotspots. Crocodiles appeared in Canada. Fossils of Wanaganosuchus, a crocodilian that normally lived in subtropical swamps, have been found on Ellesmere Island within the Arctic Circle. That's not an outlier. That's the norm. For 100,000 years, the Arctic was a jungle, and the mammals? They shrank rapidly. In the Bighorn Basin of Wyoming, one of the most complete geological records of the PETM, paleontologists have tracked the size of early horse ancestors through the temperature spike. These animals, about the size of a modern retriever at the start of the PETM, shrank to the size of a house cat within 50,000 years. Why? Because smaller bodies have a higher surface area to volume ratio. They lose heat more efficiently. In an overheated world, being small was an advantage. As soon as the temperature dropped back to normal, they grew large again, evolution responding in real time. But the PETM wasn't just about heat. It was about instability. The climate didn't spike and stay high. It fluctuated wildly. Carbon was entering the system faster than natural processes could remove it. But those processes, weathering of rocks, burial of organic matter, were still working. They just couldn't keep up. For 200,000 years, the planet oscillated between extremely hot and slightly less extremely hot, and ecosystems had to constantly adapt. And here's the thing that should terrify us. The PETM happened slowly by our standards. The carbon release took 10 to 20,000 years. That gave species time to migrate, time to adapt, time to evolve. And still, 30 to 50% of deep-sea species went extinct. Still, ecosystems were fundamentally altered. Still, it took the planet 2 million years to fully recover. We are currently releasing carbon at a rate 100 times faster than the PETM. 100 times. The comparison isn't alarmist. It's mathematical. Since 1750, humanity has burned enough fossil fuels to release 1,700 gigatons of carbon. We're currently adding about 40 gigatons per year. At that rate, we'll match the PTM's total carbon release in less than 2 centuries. But we're doing it in 200 years, not 20,000. The planet has no time to adjust. Ecosystems have no time to migrate. Species have no time to evolve. And just like the Paleocene, we're seeing the methane. In the East Siberian Arctic shelf, underwater methane plumes are already rising. In Siberia, craters over a kilometer wide have appeared where permafrost melted and trapped. Methane exploded to the surface. The feedback loop that drove the PETM is beginning again. We're not heading toward a tipping point. We've already crossed several. But let's return to the Paleocene. Because the PETM, as catastrophic as it was, eventually ended. The carbon cycle stabilized. The methane broke down. The oceans absorbed the excess CO2, and over millions of years, it was locked away in limestone and organic sediments. The temperature dropped. The ice caps, which had been absent for tens of millions of years, began to form again at the poles. And life, as it always does, adapted. The mammals that survived the PETM were different from the ones that had existed before. They were more diverse, more specialized, more modern. The early Eocene, the period immediately following the PETM, saw the emergence of the first true primates, the first horses, the first bats, the first whales. All of these groups trace their origins to survivors of the PETM. In a sense, the PETM didn't just test life, it refined it. And that brings us to the final uncomfortable truth. Every mammal alive today, including us, is the descendant of an organism that survived 2 apocalypses. The asteroid that killed the dinosaurs, and the PETM that nearly broke the climate system. Our ancestors made it through both. They were small, adaptable, opportunistic, and incredibly lucky. Because luck in evolution matters just as much as fitness. We are not separate from this story. We are part of it. The same carbon cycle that drove the PETM is the one we're disrupting now. The same feedback loops that turned the Paleocene into a hothouse are the ones we're triggering in the Arctic. The same ocean acidification that killed 30% of deep-sea species is happening right now, measurably, in every ocean on Earth. But here's the difference. The Paleocene had no choice. Volcanoes erupted. Methane was released. The planet heated. There was no intelligence, no agency, no ability to stop it. We do have a choice. We understand what's happening. We have the data, the models, the technology to change course. Whether we will is another question entirely. The Paleocene teaches us that the Earth doesn't need saving. It will be fine. Life will survive. It always has. What won't survive is the world we've built, the stable climate that allowed human civilization to flourish, the coastlines where our cities sit, the ecosystems that provide our food. If we push the planet too far, it will simply move on without us, just as it moved on without the dinosaurs. And 10 million years from now, something else will have taken our place, sifting through the fossils of our cities, wondering what happened to the species that almost understood its own power but chose not to use it. Because that's the real lesson of the Paleocene. Catastrophe isn't the end, it's a transition. The asteroid didn't destroy life, it rearranged it. The PETM didn't destroy life, it tested it. And the survivors, the ones that adapted, became something new. The question we have to answer now is whether we want to be among the survivors or among the fossils. The Arctic drilling rig pulls up another core sample. More methane bubbles rise. The scientists take notes, record the data, and prepare their reports. And somewhere, deep beneath the permafrost, ancient carbon that has been locked away for 56 million years begins to stir. History, as they say, doesn't repeat, but it rhymes. And right now, the Earth is speaking in a very familiar meter. The recovery from the PETM didn't happen overnight. It wasn't a switch that flipped, returning the planet to normal. It was a slow, grinding process that took 2 million years. 2 million years of the carbon cycle working overtime, pulling excess CO2 out of the atmosphere through chemical weathering, through the growth and burial of organic matter, through the slow accumulation of carbonate sediments on the ocean floor. The scars of the PETM are still visible in the geological record, a thin band of clay enriched in carbon isotopes found in sediment cores from every ocean basin on Earth. It's a reminder that what goes up doesn't always come down quickly. But while the climate was stabilizing, life was doing what it does best: adapting, diversifying, filling every available niche. The world that emerged from the PETM was fundamentally different from the one that had entered it. The survivors weren't just lucky. They were the ones best suited to a world of temperature extremes, acidic oceans, and unpredictable resources. And they became the foundation for everything that followed. In North America, the forests were changing. The Paleocene had been dominated by primitive flowering plants, conifers, and ferns. But the early Eocene saw the rise of more modern plant families. Legumes appeared, plants capable of fixing nitrogen from the atmosphere, enriching soils that had been nutrient-poor since the asteroid impact. Grasses were still absent, but the groundwork was being laid for their eventual arrival. The forests were denser, more complex, more productive, and with more productivity came more herbivores. The earliest true horses appeared during this time. Not the large, fast animals we think of today. These were tiny. Eohippus, also called Hyracotherium, was about the size of a fox terrier, stood maybe 40 centimeters tall at the shoulder, and had 4 toes on its front feet and 3 on its back. It didn't run across open plains because there were no open plains. It lived in forests, browsing on soft leaves and fruits, hiding from predators in the dense undergrowth. But it was a horse, the first horse. And from this small, unremarkable creature, every horse, zebra, and donkey that has ever existed would eventually descend. At the same time, the first primates that looked recognizably like primates began to appear. These weren't the lemurs and monkeys we're familiar with today. They were something stranger. Notharctus, found in Wyoming, had a long tail, grasping hands, and forward-facing eyes. It lived in trees, leaping from branch to branch, eating fruit and insects. Its brain was larger, relative to its body size, than earlier mammals. It had stereoscopic vision, which allowed it to judge distances accurately, a crucial adaptation for life in the canopy. And crucially, it had opposable thumbs. It could grip. That one adaptation, the ability to grasp a branch, to manipulate objects, would eventually lead to tool use, to culture, to us. But the most extraordinary innovation of the early Eocene wasn't happening on land. It was happening in the water. Because around 50 million years ago, a group of small hoofed mammals that lived near rivers and coastlines began spending more and more time in the water. They were probably escaping predators or searching for food or cooling off in the intense heat. Whatever the reason, they started adapting. Their legs shortened, their tails lengthened, their nostrils migrated toward the top of their heads. Over the course of 10 million years, they stopped being land animals entirely. They became whales. The earliest whales, like Pachycetus, still had legs, 4 of them. They could walk on land, albeit awkwardly. But they spent most of their time in shallow water, hunting fish. A few million years later, we get Ambulocetus, the walking whale. It looked like a crocodile with fur, about 3 meters long, with webbed feet and a powerful tail. It could swim, but it could also haul itself onto land to rest and give birth. And then came Basilosaurus, a fully aquatic whale 18 meters long, with vestigial hind legs so small they were useless for locomotion. Those tiny legs are proof of its terrestrial ancestry, a reminder that evolution doesn't erase the past, it just buries it under new adaptations. And here's the astonishing part. This entire transition from a 4-legged land mammal to a streamlined, fully aquatic predator happened in less than 10 million years. That's faster than almost any other major evolutionary transition we know of. The oceans, still recovering from the PETM, were full of fish, but had no large predators. The marine reptiles were gone. The niche was empty, and whales improbably filled it. But while whales were taking over the oceans, something else was happening on land. Carnivores were getting serious. The early Paleocene predators, the Arctocyon and their relatives, were generalists, capable of eating meat, but also perfectly happy scavenging or eating plants. They were opportunists. But by the early Eocene, true carnivores had evolved. Myiacids, small weasel-like animals with sharp teeth and retractable claws, were the ancestors of all modern carnivores. Dogs, cats, bears, seals, everything. They were small, rarely larger than a house cat, but they were efficient. They hunted in packs, they ambushed prey, they could climb trees. They were, pound for pound, the most dangerous animals of their time. And then there were the creodonts. These were not related to modern carnivores, despite looking superficially similar. They were a completely separate lineage, and for a while they were dominant. Hyenodon, which appeared in the Middle Eocene, was the size of a wolf, with jaws powerful enough to crush bone. Sarcastodon, which lived in Asia, was even larger, comparable to a modern bear. These were apex predators, and they ruled for 20 million years. But eventually they were outcompeted by the Myiacids and their descendants. Why? Because creodonts had one fatal flaw. Their teeth didn't grow back. If a creodont broke a tooth, it was crippled for life. Myiacids, and the carnivores that evolved from them, had more replaceable teeth, more efficient jaws, better brains. Slowly, over millions of years, creodonts declined and disappeared. Evolution is a competition, and sometimes the difference between winning and losing is as simple as dentition. But not all predators were mammals. In South America, which was still isolated from the rest of the world, birds had taken over the role of apex predator. The terror birds, or Forus racids, were the most successful large predators the continent had ever seen. The largest species, like Kelenken, stood 3 meters tall, weighed half a ton, and had a skull the size of a horse's. Their beaks were hooked and razor-sharp, capable of delivering bone-crushing blows. They couldn't fly, but they didn't need to. They could run at speeds exceeding 50 kilometers per hour, and they hunted in open woodlands and scrublands, chasing down mammals that had no defense against something so large and fast. For 15 million years, terror birds were unchallenged. South America had no large mammalian predators to compete with them. But that would change dramatically when the Isthmus of Panama rose from the sea and connected North and South America. When that happened, 3 million years ago, placental carnivores from the north flooded into South America. Big cats, bears, dogs. The terror birds, which had ruled for so long, couldn't compete. Within a few million years, they were gone. But during their reign, they proved something important. You don't need to be a mammal to be an apex predator. You just need to be good at killing. And speaking of killing, the Eocene wasn't just a time of innovation. It was also a time of gigantism. The trend that had started in the Paleocene toward larger and larger body sizes continued and accelerated. Mammals that had been the size of dogs were now the size of rhinos. Mammals that had been the size of rhinos were now the size of elephants. And by the end of the Eocene, some were even larger. Embolotherium, a strange herbivorous mammal from Mongolia, had a massive bony battering ram on its skull, probably used for combat with rivals. It weighed over 2 tons. Brontotherium, found in North America, was even larger, with a Y-shaped horn and a body like a tank. These weren't related to modern rhinos, despite the superficial resemblance. They were Brontotheres, a family that evolved, flourished, and went extinct entirely within the Eocene. They're a reminder that evolution is full of experiments, and not all of them succeed in the long term. But the champion of Eocene gigantism wasn't a bronto there. It wasn't even a land animal. It was a snake. Titanoboa, which we mentioned earlier, wasn't just the largest snake of the Paleocene. It persisted into the early Eocene, growing even larger as the climate warmed. 13 meters, over a ton, capable of swallowing a crocodile whole. It's difficult to overstate how bizarre this animal was. Modern anacondas are impressive, but they're dwarfed by Titanoboa. If you stood next to one, its body would be thicker than your torso. Its head would be the size of a watermelon. And it lived in rivers and swamps, ambushing prey from below, constricting with enough force to stop a heart in seconds. Why did it get so large? Temperature. Snakes are ectothermic. They rely on external heat to regulate their body temperature. The warmer the environment, the more energy they have, the faster they grow, the larger they can become. Titanoboa's size tells us that the average temperature in northern South America during the early Eocene was at least 32 to 34 degrees Celsius year-round. That's a jungle so hot that most modern mammals couldn't survive there. But Titanoboa thrived, and it wasn't alone. The Eocene tropics were filled with giants. Crocodiles over 6 meters long, turtles with shells 2 meters in diameter, fish the size of small cars. The food chains were dense, the productivity was off the charts, and size was the strategy that worked. Because in a world without significant temperature stress, without seasonal droughts, without ice ages, the only limit on body size was food availability. And food in the Eocene was everywhere. But the Eocene couldn't last forever. Around 34 million years ago, something changed. The Drake Passage, the gap between South America and Antarctica, finally opened wide enough for ocean currents to flow through. For the first time in over 100 million years, water could circulate completely around Antarctica without hitting land. And when that happened, the Antarctic Circumpolar Current formed. This current isolated Antarctica from the warmer waters of the rest of the world. The continent cooled. Snow began to accumulate. And within a few 100,000 years, Antarctica was covered in ice. This wasn't just a local event. The formation of Antarctic ice sheets locked up enormous amounts of water, lowering global sea levels by over 60 meters. The climate, which had been warm and stable for tens of millions of years, began to cool. The hothouse world of the Eocene gave way to the icehouse world of the Oligocene. And life, once again, had to adapt or die. The transition from the Eocene to the Oligocene, known as the Grande Coupure in Europe, was marked by massive extinctions. Many of the strange, archaic mammals that had dominated the Eocene disappeared. The Brontotheres, gone. The creodonts, in decline. The giant birds of Europe, extinct. In their place came more modern forms. The ancestors of deer, pigs, camels, and rhinoceroses spread across the northern continents. These were faster, more efficient, better adapted to the cooler, more seasonal climates. And for the first time, grasslands began to appear. Not everywhere, not yet, but in isolated patches in Central Asia and North America. Grasses are tough, fibrous, and full of silica. They're difficult to digest and even harder to chew. Most herbivores couldn't handle them, but some could. And those that could suddenly had access to a food source that was abundant, resilient, and previously untapped. The age of grazers was beginning. But here's the part that connects back to the Paleocene, to the PETM, to the story we started with. Every major group of modern mammals, every family, every order, can trace its origins back to the survivors of the Paleocene. The primates that would become us, the ungulates that would become horses and elephants, the carnivores that would become lions and wolves, the cetaceans that would become whales and dolphins. All of them emerged from the chaos that followed the asteroid. All of them were tested by the PETM. And all of them survived because they were adaptable, because they could handle instability, because they were good at finding a way forward when the world was falling apart. And that brings us back to the present, because we are, in a very literal sense, the inheritors of that chaos. Our intelligence, our adaptability, our ability to manipulate our environment, all of it comes from ancestors that had to survive catastrophe. The Paleocene taught our lineage how to be resilient. The PETM taught it how to adapt to rapid climate change. And now, 66 million years later, we're facing a similar test. Except this time, we're the ones causing it. The carbon we're releasing isn't coming from volcanoes. It's coming from us. The methane bubbling up in the Arctic isn't a natural process. It's a consequence of warming that we initiated. The ocean acidification, the rising temperatures, the feedback loops, all of it is familiar. We've seen it before, written in the rocks, preserved in fossils, undeniable. And the outcome, if we follow the same trajectory, is equally clear. The planet will survive. Life will survive. But the world we know, the stable climate that made agriculture possible, that allowed cities to grow, that gave us 10,000 years of relative peace, that world is not guaranteed. The Paleocene recovery took 2 million years. We don't have 2 million years. We have decades, maybe less. The methane in Siberia, the ice melting in Greenland, the currents shifting in the Atlantic. These aren't future problems. They're happening now. And unlike the organisms of the Paleocene, we can't migrate to the poles and wait it out. The poles are melting. There's nowhere to go. But here's the uncomfortable truth that the Paleocene also teaches us. Catastrophe creates opportunity. The asteroid that killed the dinosaurs gave mammals their chance. The PETM, as devastating as it was, led to the emergence of modern mammal groups. Destruction and creation are two sides of the same coin. The question is, what are we creating? Because right now, we're at a crossroads. We can continue on our current path, burning fossil fuels, releasing carbon, triggering feedback loops we don't fully understand, and see what happens. Maybe we adapt. Maybe we don't. Maybe future species will look back at us the way we look at the mammals of the Paleocene, survivors of a bottleneck, the lucky ones who made it through. Or maybe they'll look at us the way we look at the dinosaurs, dominant, successful, and utterly unprepared for the catastrophe they didn't see coming. The drilling rig in Siberia continues its work. The scientists continue taking samples. The methane continues to rise. And the planet, indifferent to our concerns, continues its slow march through geological time. It's been here for 4.5 billion years. It will be here for billions more. The question isn't whether Earth will survive, it's whether we will. And if we do, what kind of world we'll be surviving in. Because the Paleocene wasn't just 10 million years of chaos. It was 10 million years of adaptation, innovation, and ultimately, renewal. The mammals that emerged from it weren't the same as the ones that entered. They were better, faster, smarter, more resilient. The same could be true for us, but only if we recognize the test we're facing and choose to meet it. The carbon in the atmosphere isn't just a number. It's a message from the past, a warning written in isotopes and temperature proxies and fossil plankton. It's telling us that the Earth has been here before, that it knows how this story ends, and that the ending isn't kind to species that can't adapt. We have the data, we have the science, we have the capacity to understand. What we do with that understanding will determine whether we're remembered as the species that saw the warning and changed course, or the species that saw it and did nothing. 66 million years ago, an asteroid reset the planet. 56 million years ago, the planet reset itself. And now, in the year 2024, we're running the same experiment for a third time. The only difference is, this time, we're the ones holding the match. And the question we have to answer, the only question that matters, is whether we're going to light it or put it down. The Arctic ice continues to melt. The methane continues to rise. And somewhere, deep in the rock record of the Paleocene, the answer is already written. We just have to decide if we're going to read it. The Eocene wasn't content to simply stabilize. It pushed boundaries. After the PETM's fever broke and temperatures began their slow descent, life didn't retreat into caution. It exploded. The Middle Eocene, roughly 45 to 40 million years ago, represents the absolute peak of mammalian experimentation. This was the moment when evolution threw out the rulebook and tried everything, consequences be damned. In what is now Germany, in a place called the Messel Pit, we have a snapshot of this world preserved in exquisite detail. 47 million years ago, a volcanic lake sat in a subtropical forest. Organisms that died and sank into the oxygen-depleted depths were preserved so perfectly that we can see their fur, their feathers, their stomach contents, even the color patterns on their wings. It's the Paleogene equivalent of Pompeii, except instead of a single catastrophic day, it's a window into thousands of years of an ecosystem at its peak. And what that window shows us is bizarre. There are early horses, yes, but also paleotheres, which looked like horses but weren't related. There are early primates with opposable thumbs and forward-facing eyes. There are bats, fully formed, already capable of echolocation. Not primitive proto-bats, modern bats. Which means that somewhere in the 10 million years between the Paleocene and the Middle Eocene, a group of small insectivorous mammals evolved powered flight, complex vocal apparatus for sonar, and the neurological processing to interpret echoes in real time. That's not gradual evolution. That's a revolution. But the most telling thing about Messel isn't what's there. It's what isn't. There are no large predators. The biggest carnivore in the entire ecosystem is about the size of a raccoon. Why? Because this was an island ecosystem, isolated in a shallow sea that covered much of Central Europe. And on islands, the normal rules don't apply. Without large predators, prey animals don't need to be fast or vigilant. They become complacent. And in complacency, they become experimental. This is a pattern we see repeated across the Eocene. Wherever isolation occurs, whether geographic or ecological, evolution gets weird. In Asia, a group of mammals called embrithopods evolved into something that looked disturbingly like a rhinoceros, but was more closely related to elephants. Arsinoitherium, found in what is now Egypt, had two enormous bony horns fused to its skull, side by side like the prongs of a tuning fork. It weighed 2 tons and had tusks and a trunk-like structure. But it wasn't an elephant. It wasn't a rhino. It was something else entirely, a product of Africa's isolation during the Eocene, evolving in parallel to similar forms on other continents. This phenomenon, convergent evolution, is one of the most powerful pieces of evidence we have that evolution isn't random. Give similar environmental pressures to different organisms, and they'll arrive at similar solutions. The saber-tooth morphology, elongated canine teeth for delivering fatal bites, evolved independently at least 5 times. In placental carnivores, in marsupial carnivores, in creodonts, even in a bizarre herbivorous mammal from South America that used its saber teeth to strip bark. Evolution finds what works, and it uses it, regardless of ancestry. But convergence has limits, because while multiple lineages were experimenting with the same body plans, they weren't doing it with the same efficiency. And in the long run, efficiency wins. The creodonts, which had dominated as predators for 20 million years, were losing ground to true carnivores. The archaic ungulates, which had been the primary herbivores since the Paleocene, were being replaced by more modern forms with better teeth, better digestion, better locomotion. The Eocene was, in a sense, a live audition. Evolution was testing every possible variation, and the ones that worked would inherit the future. The ones that didn't would become footnotes. And then there was the slow, creeping realization that the world was changing in a way it hadn't for 60 million years. It was getting colder, not dramatically, not catastrophically, but steadily, inexorably, the temperatures that had been stable since the Cretaceous were beginning to decline. The cause was tectonic. India, which had been an island continent drifting north for millions of years, collided with Asia. The impact crumpled the Earth's crust like tissue paper, pushing the Himalayas and the Tibetan Plateau upward at a rate of several centimeters per year. Within 10 million years, the Himalayas were the tallest mountain range on Earth, and mountains change climate. When moist air from the Indian Ocean hits a mountain range, it's forced upward. As it rises, it cools. As it cools, the water vapor condenses and falls as rain. The Himalayas created the monsoon system that still dominates South Asia today. But more importantly, they created a massive surface area of fresh rock exposed to the elements. And fresh rock weathers. When silicate minerals in rock are exposed to rain, they react with carbon dioxide dissolved in the water. The CO2 is converted into carbonate minerals, which eventually wash into the ocean and are buried. This process, chemical weathering, is one of the primary ways the Earth removes carbon from the atmosphere. And with the Himalayas growing taller every year, weathering accelerated. CO2 levels, which had been steady at around 1,000 parts per million since the Paleocene, began to drop. Slowly at first, a few parts per million years. But the trend was clear. The greenhouse was cooling. By 34 million years ago, at the boundary between the Eocene and the Oligocene, the atmospheric CO2 had dropped below 700 parts per million. And that was the threshold. That was the point where Antarctica, which had been ice-free for 100 million years, finally accumulated enough snow that it didn't melt in the summer. The snow compacted into ice. The ice reflected sunlight. The reflected sunlight cooled the planet further. More ice formed. It was a feedback loop, just like the one that drove the PTM, but in reverse. Within a few 100,000 years, Antarctica was covered in an ice sheet 2 kilometers thick. Sea levels dropped by 70 meters. Coastlines that had been underwater for tens of millions of years were suddenly exposed. Shallow seas drained. Land bridges appeared, and the animals that had been isolated on islands and continents were suddenly able to migrate, to compete, to interbreed. The result was chaos. In Europe, the transition is so stark that paleontologists gave it a name: the Grande Coupure, the Great Cut. In a geological instant, the old Eocene fauna disappeared. The Paleotheres, the early primates, the archaic carnivores, gone, replaced by immigrants from Asia, modern rhinoceroses, early pigs, advanced carnivores. These newcomers were faster, more efficient, better adapted to the cooler, more seasonal climate. They didn't outcompete the native species. They annihilated them. But in other places, the transition was less abrupt. In North America, the cooling was gradual. Forests gave way to more open woodlands. Woodlands gave way to savannas. And for the first time, grasslands appeared. Not the vast prairies we think of today, just patches scattered across the Great Plains and the Central Valleys. But those patches were enough, because grass, as a food source, changes everything. Grass is terrible to eat. It's fibrous, tough, and loaded with silica, which wears down teeth faster than almost any other plant material. Most herbivores can't handle it. Their teeth aren't strong enough. Their guts aren't specialized enough. But some herbivores evolved adaptations, high-crowned teeth that continued growing throughout life, compensating for wear. Complex, multi-chambered stomachs filled with symbiotic bacteria capable of breaking down cellulose. Longer intestines for more efficient digestion. These animals, the first true grazers, had access to a food source that was abundant, fast-growing, and underutilized. They thrived. And with them came a new kind of predator. Because grazers living in open grasslands couldn't hide. They had to be fast. And predators hunting in open grasslands couldn't ambush. They had to be faster. The arms race between predator and prey, which had been simmering for millions of years, suddenly accelerated. Herbivores developed longer legs, more efficient running gaits, better stamina. Carnivores did the same. Speed became the defining characteristic of success. By the Miocene, 20 million years ago, the world looked recognizably modern. The mammals were modern. The plants were modern. The climate, while warmer than today, was within the range of what we'd consider normal. The age of giants was ending. The age of specialists had begun. And with specialization came vulnerability. Because specialists, by definition, are adapted to specific conditions. When those conditions change, they struggle. And change was coming. The Miocene was relatively stable, but it was building towards something. The ice sheets in Antarctica weren't shrinking, they were growing. And in the high latitudes of the northern hemisphere, the first glaciers were beginning to form. Not continent-spanning ice sheets, not yet, but the seeds were there. And when the climate tipped, when the CO2 dropped just a little further, those seeds would germinate into the ice ages that would define the Pleistocene. But before we get there, there's one more chapter in the story of post-dinosaur life that needs to be told. Because while the northern continents were cooling and drying, and giving rise to grasslands and grazers, South America remained isolated. It had been cut off from North America since the Paleocene, and it would remain cut off for another 25 million years. And in that isolation, it evolved an ecosystem unlike anything else on Earth. South America in the Miocene was dominated by mammals we don't have names for, because they have no living relatives. The largest herbivores weren't ungulates. They were not ungulates, a group that looked superficially like horses or rhinos, but were only distantly related to either. Some had claws instead of hooves. Some had trunks. Some had teeth that grew continuously, like rodents. They were evolution's rough draft, the version that worked in isolation but would fail when tested against the global standard. The predators weren't cats or dogs. They were marsupials. Thylacosmilos, a saber-toothed marsupial, looked almost identical to Smilodon, the famous saber-toothed cat that would later invade from the north. Same body plan, same elongated canines, same ambush predator strategy. But it wasn't related. It was a marsupial, more closely related to kangaroos than to cats. It's one of the most striking examples of convergent evolution we have. Two completely different lineages, separated by 100 million years of evolutionary history, arrived at the exact same solution to the problem of how to kill large prey. And then there were the terror birds, Phorus racids. We mentioned them earlier, but by the Miocene they had reached their peak. Kelenken, the largest species, had a skull 70 centimeters long. Its beak could generate bite forces comparable to a large crocodile. It stood 3 meters tall and weighed close to 500 kilograms. It was fast, intelligent, and utterly dominant. For 15 million years, terror birds were the apex predators of an entire continent. No mammal could challenge them, not because mammals weren't capable, but because South America's mammals had never evolved the size or speed necessary to compete. The terror birds had gotten there first. But isolation is a double-edged sword. It allows unique ecosystems to develop, free from outside competition. But it also makes those ecosystems fragile. Because when the isolation ends, when the barriers come down, the isolated species have to compete with organisms that have been tested by global pressures. And very often, they lose. 3 million years ago, the Isthmus of Panama rose from the sea. For the first time in over 60 million years, North and South America were connected. And the result was one of the most dramatic ecological upheavals in Earth's history. We call it the Great American Biotic Interchange, and it was less of an exchange and more of an invasion. From North America came mammals that had been honed by millions of years of competition on the largest, most diverse landmass on Earth. Cats, dogs, bears, camels, horses, deer. They poured into South America and found an ecosystem that had never seen anything like them. The notungulates, slow and specialized, were outcompeted within a few 100,000 years. The terror birds, which had ruled for so long, were driven to extinction by jaguars and wolves. The marsupial predators disappeared entirely, unable to compete with placental carnivores that were faster, smarter, and more efficient. South America did send some species north: opossums, armadillos, porcupines, ground sloths. But the traffic was overwhelmingly one way. North American mammals displaced or exterminated most of South America's native fauna. It's a sobering reminder that in evolution, success is relative. The notungulates and terror birds weren't failures. They were successful for tens of millions of years. But when the context changed, when they were forced to compete with species that had been tested by harsher conditions, they couldn't adapt fast enough. And this brings us to the final phase of the story, the Pleistocene, the Ice Ages. Because by 2.5 million years ago, the slow cooling that had begun in the Eocene finally reached a tipping point. The Greenland ice sheet formed, the Arctic Ocean froze, and the Earth entered a period of extreme climate instability unlike anything it had experienced since the asteroid impact. The Pleistocene wasn't a single ice age. It was a series of glacial cycles driven by subtle changes in Earth's orbit. Every 100,000 years or so, the tilt and wobble of the planet's axis would shift just enough to change the distribution of solar radiation. When the northern hemisphere received slightly less sunlight during summer, snow that fell in winter didn't fully melt. It accumulated. Year after year, the ice sheets grew. They spread south from the Arctic, covering Canada, Scandinavia, and northern Asia under kilometers of ice. Sea levels dropped by 120 meters. Coastlines expanded. Land bridges appeared. And then, after tens of thousands of years of cold, the cycle reversed. The orbit shifted again. Summer sunlight increased. The ice melted. Sea levels rose. The glaciers retreated. And for 10 or 20,000 years, the climate was warm, almost as warm as it is today. And then the cycle began again. Cold, warm, cold, warm, over and over for 2.5 million years. Life, predictably, had to adapt or die, and many species died. The Pleistocene extinctions are still being debated, but the pattern is clear. Large mammals, megafauna, were disproportionately affected. In North America, we lost mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, and dozens of other species. In South America, the losses were even worse. In Australia, every land animal over 40 kilograms went extinct. In Eurasia, we lost woolly rhinos, cave bears, and giant elk. The question is why? And the answer is complicated. Climate change played a role. As the glaciers advanced and retreated, habitats shifted. Tundra became forest. Forest became grassland. Grassland became desert. Species that couldn't migrate fast enough or adapt to new conditions disappeared. But climate alone doesn't explain the pattern. Because the Pleistocene had seen glacial cycles for over 2 million years. Megafauna had survived dozens of cycles. So why did they all go extinct in the last one? The answer, uncomfortably, is us, humans. Homo sapiens evolved in Africa around 300,000 years ago. For most of that time, we stayed in Africa and parts of the Middle East. But starting around 70,000 years ago, we began to spread into Asia, into Europe, into Australia, and finally, around 15,000 years ago, into the Americas. And wherever we went, megafauna extinctions followed. Not immediately, not always in perfect correlation. But the pattern is undeniable. In Australia, megafauna survived for millions of years through multiple glacial cycles. They went extinct within a few thousand years of human arrival. In North America, mammoths and mastodons survived the last glacial maximum, which was the coldest point of the entire Pleistocene. They went extinct 11,000 years ago, right when human populations were expanding and developing advanced hunting techniques. In Madagascar, giant lemurs and elephant birds survived until humans arrived 1,500 years ago. Within a few centuries, they were gone. The evidence is circumstantial, but it's overwhelming. Humans didn't cause all the Pleistocene extinctions. Climate played a role. But we were the final stressor, the additional pressure that pushed species already struggling with habitat loss over the edge. And here's the part that ties back to the Paleocene, to the PETM, to the asteroid. Every major extinction event in Earth's history has been followed by a recovery. Life rebounds. New species evolve to fill the empty niches. The planet heals. But recovery takes time, millions of years. The Paleocene recovery took 10 million years. The recovery from the Permian extinction, the worst in Earth's history, took 15 million years. We don't have that kind of time. We have decades. We are currently living in the immediate aftermath of the Pleistocene extinctions. The megafauna are gone. The ecosystems they supported are gone. And we've had 11,000 years to adjust. That's nothing. Geologically, ecologically, it's the blink of an eye. We're living in a world that's still in shock, still reeling from the loss of species that shaped entire landscapes. And now, on top of that, we're changing the climate faster than it's changed since the PTM. We're releasing carbon at a rate 100 times faster than the event that nearly broke the climate system 56 million years ago. The methane in Siberia is escaping. The ice in Greenland is melting. The feedback loops are tightening. We're not heading toward a tipping point. We've already crossed several. But here's the difference between us and every other species that has faced extinction. We understand what's happening. We can measure it, we can model it, and we have, in theory, the capacity to stop it. The Paleocene mammals didn't choose to survive. They were lucky, adaptable, and in the right place at the right time. We're not relying on luck. We're relying on choice. The solutions exist. Renewable energy, reforestation, carbon removal, sustainable agriculture. We know what needs to be done. The technology is proven. The economics are increasingly favorable. What's missing is the collective will to deploy these solutions at the scale and speed required. We need to halve global emissions by 2030. That's 6 years from now. It's not impossible. But it requires treating this as the existential crisis it is. And yet, for decades, we've known. We've had the data. We've understood the mechanisms. And emissions have continued to rise. Because changing systems is hard. Because fossil fuels are profitable. Because humans are phenomenally bad at responding to long-term diffuse threats. We see immediate dangers and react. But a problem that unfolds over decades, we rationalize, we delay, we assume someone else will handle it. But there is no someone else. There's just us. 7.8 billion people on a planet with finite resources and a climate system we've destabilized. And the clock is not slowing down. The Paleocene teaches us that the Earth doesn't need saving. It will be fine. Life will survive. It always has. What won't survive is the world we've built. The stable climate that allowed agriculture, cities, and civilization to flourish. If we push the planet too far, it will simply move on without us, just as it moved on without the dinosaurs. And 10 million years from now, something else will have taken our place, sifting through the fossils of our cities, wondering what happened to the species that understood its own power but chose not to use it. Because that's the lesson. Catastrophe isn't the end. It's a transition. The asteroid didn't destroy life. It rearranged it. The PETM didn't destroy life. It tested it. And the survivors became something new. The question we have to answer now is whether we want to be among the survivors or among the fossils. The Arctic drilling rig pulls up another core sample. The methane bubbles rise. The scientists take notes and file their reports. And somewhere, deep beneath the permafrost, ancient carbon that has been locked away for 56 million years continues to stir. History doesn't repeat, but it rhymes. And right now, the Earth is speaking in a very familiar meter. 66 million years ago, an asteroid reset the planet. 56 million years ago, the planet reset itself. And now, in the year 2024, we're running the same experiment for a third time. The only difference is, this time, we're the ones holding the match. The question, the only question that matters, is whether we're going to light it or put it down. We're standing at a boundary. The KPG boundary marked the end of one world and the beginning of another. We're creating our own boundary right now. And millions of years from now, when future geologists study the rocks, they'll see a thin layer, a layer of plastic, concrete, and carbon. The Anthropocene boundary. And they'll ask, which side did we choose? The answer isn't written yet, but it's being written right now. In every choice we make, every policy we implement, every ton of carbon we emit or avoid. The Paleocene showed us that life can survive the worst catastrophes. But survival and thriving are not the same thing. We have the knowledge, the technology, and the capacity to choose a different path. Whether we have the wisdom and the will remains to be seen. The story of the Paleocene is a story of resilience. The story of the PETM is a story of consequences. The story of the Pleistocene is a story of power and responsibility. And the story of the Anthropocene, our story, is still unfolding. The ending hasn't been decided, but the author is us, and the deadline is closer than we think.